All right, this is a problem from our equilibrium module. And it's sort of a made-up problem, but it's to get us comfortable with ice tables. We learned back in Chem 1 that you could look at a reaction and determine, for example, a limiting reagent problem or something like that by comparing the mole-to-mole ratio, essentially is what you did for limiting reagents. So in this module, when we throw in equilibrium and we now know, well, the reaction doesn't always go to completion, we can do a similar sort of step, a similar sort of procedure to determine what's left at equilibrium. And so we're going to use an ice table. You may or may not have used it during Chem 1, but an ice table is essentially a way for us to keep track of what's going on in the reaction. So I've got this reaction. Let me write it over here larger. It is in terms of X's and Y's. It's just a generic reaction to give us some odd numbers to play with. And I'm going to set up a table with an initial, a change, and an equilibrium amount. The change I usually write as the symbol delta, but of course the word change starts with C, and that's why these are called ice tables. I am going to do this ice table in moles because that is what is given. If, of course, I need to relate this to an equilibrium constant, I might want to do it in molarity because equilibrium constants need the concentrations. To calculate the equilibrium constant, you need the concentrations in molarity. So, but I'm going to do this in moles. I am starting a reaction, all right, with 15 moles of X and 14 moles of Y. They're allowed to react according to the reaction below. You'll notice it did not say anything about the amount of Z. So the assumption is if the product isn't mentioned, assume that you start with 0 of it. Typically, that's how we run a reaction. You dump together the reactants and then they form the products. Because we're looking at equilibrium reactions, the reality is that sometimes we may start with some product. So just pay attention to what your instructions tell you, what is given in the problem. If nothing is mentioned about a starting amount of a product, the assumption is that amount is 0. So I've got 15 moles of X, 14 moles of Y, and 0 moles of Z initially at the beginning of this reaction. The question is how many moles of X are at equilibrium? There is my equilibrium row, and I want to know how many moles of X. So I'm essentially looking for this value down here. If there are 8 moles of Y left at equilibrium, which means at equilibrium, here in the equilibrium row, I have 8 left of Y. And that's the only other number that it tells me besides the reaction. As we learned in Chem 1, and this should make sense to you, if I start with 14 moles of Y initially, and there are 8 moles of Y at equilibrium, that means that the difference between those two is what actually reacted. And 14 minus 8, you can do that in your head if you want to, or you can plug it into a calculator. That means that 6 moles of Y actually reacted. So the change is a -6 because the 6 moles are going away. They're disappearing. So that's why I put a -6 in the change. 14 minus 6 equals 8. From Chem 1, we learned that as this reaction proceeds, if 6 moles of Y actually reacted, then I can calculate, well, how many moles of X does it take to react with that many moles of Y? So how many moles of X react with 6 moles of Y? Then I would multiply by the mole-to-mole ratio. Let me make that multiplication a dot symbol so that I don't confuse it with my X. I need moles of Y on the bottom, moles of X on top, and then the numbers that I put here is the mole-to-mole stoichiometry from the reaction. And so there are 2 moles of X that are formed for every 3 moles of Y that react. 6 times 2 is 12, divided by 3 is 4 moles of X will react in that case. So if 6 moles of Y actually reacted, and I know this because I started with 14, I ended up with 8, then based on the mole-to-mole stoichiometry, that means 4 moles of X reacted, which means, let me switch colors, that means I put a -4 in the change for X. And if I start with 15 and 4 moles of it react, at equilibrium, I have 11 moles of X remaining. Now, this problem doesn't ask for it, but we could go on and determine the amount of Z at equilibrium, because sometimes you might need to know that. And we would do it the same way. We would say, okay, how many moles of Z if 6 moles of Y react? So if 6 moles of Y react, how many moles of Z will be formed, because it's a product? Moles of Y on the bottom, moles of Z on the top. I use the stoichiometry here. I use the 4 and the 3 in the stoichiometry. So 4 over 3, that's a 4, sort of. And that answer is 8. That means 8 moles of Z are formed during this process, which means the change is +8. It is plus on this side because that amount is forming, which means at equilibrium, there are 8 moles of Z. This change row, where am I? There we go, is the stoichiometry. This is the stoichiometry of the reaction.